Hello, my name is Takatoshi Sakazaki from Kyoto University. Today I'd like to talk about an array of ringing global free modes discovered in tropical surface pressure data. So this is about the atmospheric normal mode oscillations. And the present results will be published very soon in JAS, so please find this paper if you are interested in details. So let's start with an introduction. The free oscillations, or global normal modes, are waves that continue to exist with an eigenfrequency and the corresponding spatial structure after being excited by some external force. And one example is the vibrations of circular membrane like dichotrons. The superposition of different normal modes produces nice music. The same thing happens in a real atmosphere, even though it's much more complicated. And this issue is treated by the so-called classical tidal theory. So we consider linearized primitive equations about the background atmosphere with zero background winds and the temperature as a function of only height. And in this case, solutions are separable and are represented as superposition of Hough modes. Here, the vertical structure is obtained by solving the vertical structure equations, like this, with appropriate boundary conditions. On the other hand, meridional structure is obtained by solving the Laplace tidal equations, and this is called Hough functions. Here, note that these two equations are coupled through the separation constant h, which is sometimes called equivalent depth. So in case of free oscillations, we consider homogeneous solutions without any forcing, like this. And then in this case, the vertical structure equation become the eigenvalue problems, and we can get the equivalent depth h and the vertical structure w as eigenvalues and eigenvectors respectively. And then by using this value h, next we solve the Laplace tidal equations for each Zonal wave number, and we can get the frequency and the meridional structure as eigenvalues and eigenvectors respectively. First, for the vertical structure equation, for the isothermal atmosphere, it is known that we can get the analytical solutions. In this case, h is almost 10 km, and vertical structure has a so-called Lam wave structure, whose energy is trapped near the surface. And this is almost true for realistic temperature profile cases. Some studies, by using numerical estimations, suggest that the h is again almost 10 km and the vertical structure is similar to the Lam wave structure, almost barotropic. But here, note that there is only a single values for equivalent depth, which is about 10 km, even for the realistic temperature profile. Then, next, by using the value of h, we solve the Laplace tidal equations. And this is eigenfrequency as a function of zonal wave number. And this is a case for symmetric components with respect to the equator. And we have Rossby modes, Kelvin modes, and inertial gravity wave modes. Of course, each frequency has a corresponding meridional structure, a function. And here shown are some examples. This is a Rossby wave mode. And this is a Kelvin wave mode as a function of latitude. Now this is the same as the previous figure, but we also show the anti-symmetric components. And here we have a Rossby gravity wave mode here. The question here is that can these modes corresponding to the equivalent depth of 10 km be identified in a real atmosphere? In previous studies, because of the temporal resolution of the measurements, which is about 1 cycle per day, most previous studies considered low-frequency modes, especially Rossby modes, such as 5-day wave, 4-day wave, and 10-day wave, and only a few Kelvin waves and Rossby gravity wave modes, such as 33-hour Kelvin wave and a 2-day wave. And the most well-known example is a 5-day wave. This is a Rossby wave mode. And Madden and Julian, one of the pioneers of the normal mode studies, and found the westward propagating wave number 1 wave by analyzing the surface pressure data. And they found that the meridional structure is quite close to the Hough functions of the 5-day wave. And a later study by using the satellite datasets actually showed that the vertical structure is quite close to the so-called Lam wave. So now this is recognized as a manifestation of a normal mode Rossby wave. So by contrast, there have been only a few studies about high-frequency modes, except for a couple of Kelvin modes, including 33-hour wave and gravity wave modes, a few gravity wave modes whose existence was first suggested by Hamilton and Garcia using the frequency spectrum for the surface pressure data at Jakarta. And anyway, to summarize, the observational evidences of normal modes have been obtained only less than 10 modes, mostly for Rossby modes and a few Rossby gravity in the Kelvin and the gravity wave modes. But of course, this covers only a portion of the full array of global normal modes. So what we will do in this study is, by using the ERA 5 hourly surface pressure dataset, we will demonstrate that the atmosphere exhibits much more normal mode oscillations than previously identified. This is a description about dataset and analysis methods. We used ERA 5 surface pressure and geopotential for 38 years. And for the analysis methods, we first prepared meridionally averaged tropical symmetric and anti-symmetric components. And by using these datasets, zonal wavenumber-frequency spectrum, two-dimensional spectrum, is calculated for each year, and the 38-year results are averaged. And by using the hourly dataset, we expect that we can identify the normal modes in this very high-frequency region. Now I will show the results, and this is the zonal wavenumber-frequency spectrum for symmetric components with respect to the equator. The left panel is from 0 cycles per day to the 12 cycles per day, which correspond to 2-hour periods. And the right panel is a zoom-in version for the low-frequency region. First, we notice that the horizontal line type of spectrum peaks, and these corresponds to the solar diurnal tide, semidiurnal tide, and even the lunar semidiurnal tide. And in addition to them, we see lots of clear discrete peaks like this, like this. And actually, when we superpose the theoretical dispersion curve for the normal mode frequency, we found that they show an implicit agreement with this theory. And this is true for the anti-symmetric components. In this case, we have Rossby gravity wave modes. And anyway, the observation, the spectral peaks show an implicit agreement with the normal mode dispersion curve. So this indicates that we identified a large array of normal modes in the surface pressure data with periods as short as 2 hours for the first time. So next, in order to investigate the meridional structure, we apply the regression analysis for each mode. Now I will show the methodology here. First, we define for each mode we define the index time series as futures time series at 0 degrees in longitude. For this, we use the meridional average data for tropical region. And this is an example for the index time series. And next, by using a global surface pressure data, these data are regressed onto this index time series, and we can get this kind of map. And then for presentation, we define the amplitude and the phase at each latitude. Here the phase is a relative phase with respect to this reference longitude. And this is the amplitude and the phase as a function of latitude. Black curves are amplitude and gray circles are phases. And finally, in order to show how the observed meridional structure is close to the theory, we fit the Hough function to the observational meridional structure, like this. And in this case, we see that the observations are very close to the theoretical Hough functions. And we did these calculations for all modes, second gravity, first gravity, and Kelvin and Rossby modes for each zonal wave number. And again, we found that the observed meridional structure is quite consistent with the theoretical Hough functions. Only exceptions may be the low-frequency Rossby modes, and this is likely because they are distorted by the background zonal winds because their phase speed is very small. And this is true for anti-symmetric modes, as shown here. Again, the observed meridional structures are quite consistent with the theoretical Hough functions, and the exceptions may be the low-frequency Rossby gravity wave modes, again, likely because they are distorted by the background zonal wind. So next, we investigate the vertical structure. Here, the geopotential data have been regressed onto the same index. Now here is the results for gravity wave mode, and the left panel is for amplitude and the right panel is for phase. And here also shown is the theoretical Lamb wave structure, and we see that the observed structure agrees quite well with the Lamb wave structures. Again, amplitude shows an exponential increase, and the phase is almost constant, indicating the barotropic structure. And this is true for all other modes, Kelvin, Rossby, and anti-symmetric gravity, and Rossby gravity wave modes. Again, some exception may be found here. Some Rossby modes and the Rossby gravity wave modes show and phase tilt, and this indicates an energy leakage, and actually these are pointed out by previous studies about the normal mode Rossby waves. So these are main results, but finally I'd like to discuss 2 points about the parameters of the spectral peaks. For this purpose, we first fit the so-called Lorentzian function to the observed spectral peak of each normal mode oscillations. By using this fitting, we can define the central frequency and the spectral width. Now we will discuss these 2 quantities. And this is about the central frequency, and here shown is the difference between the observation and the theory about the normal mode frequency as a function of wave number. And we see that the small difference is linearly dependent on zonal wave number. And this is likely explained by the Doppler shift due to the eastward background winds. Actually, these two dashed lines indicate the wave number dependency with the following relation. Here we assume the winds is 5 meters per second or 10 meters per second at the mid-latitudes. So next we will discuss the spectral width. So first, what determines the spectral width? So one possibility is a variability in the background atmosphere, such as the changes in the equivalent depth. But even if we did the same analysis for each season, we found that the seasonal cycle in central frequency was very small. So this possibility may be unlikely. So another possibility may be the dissipation. So based on the analogy to the harmonic oscillator with damping and forcing, Hamilton and Garcia estimated the damping rate based on the spectral width of the normal mode frequencies. So we will revisit this approach here. And this is the estimated effective damping scale based on the spectral width as a function of zonal wave number for symmetric and anti-symmetric modes. First, this result is broadly consistent with the estimation by Hamilton and Garcia for 33-hour Kelvin wave mode. In addition to them, we find that the damping scale is dependent on the zonal wave number, and it is longest for small wave number, but becomes shorter with increasing zonal wave number. And one possibility may be the horizontal mixing, but we have to do more work to elucidate the actual processes, and this is the future work. So to summarize, by using either 5 surface pressure datasets, we discovered that the atmosphere is ringing like a bell with the theoretically expected global normal mode frequency, which are slightly Doppler shifted by background winds. The observed meridional and vertical structure agrees quite well with the corresponding theoretical Hough functions and Lamb mode respectively. And these results provide a strong confirmation of classical tidal theory. For example, equivalent depth is about 10 km. Also, the spectral parameters, such as the spectral width, may have a very important information of the atmosphere, such as the forcing and the dissipation mechanism. So these normal mode spectral peaks may serve as a new diagnosis for atmospheric models in the future. So thank you very much for your attention.